If you want to predict the invisible forces acting between charged objects, you need a starting point, a way to anchor the abstract physics into hard numbers. This is Coulomb's law, calculating the precise force between 2 point charges. The critical feature is the inverse square relationship. By dividing the product of the charges by the square of the distance, the force diminishes rapidly as objects separate. When you introduce multiple point charges, the principle of superposition applies. We calculate the individual pull or push from each surrounding particle and then add them together as vectors to find the net force on our target. To map the electric stress in space, we define the electric field, E. This formula shows field strength in a vacuum. The field lines follow strict rules, originating from positive charges and terminating on negative ones, providing a map of direction and density. While Coulomb's law is exact for discrete, countable particles, applying this point-by-point logic to solid, macroscopic objects introduces a massive increase in complexity. In reality, a metallic surface doesn't consist of a few particles, it contains trillions of electrons. Summing every discrete vector is computationally impossible. To solve this, physics abstracts these individual particles into continuous charge distributions, treating the electricity as if it were smoothly spread across a line, a surface, or a volume. We use calculus to divide the continuous object into infinitesimally small theoretical point charges, labeled here as dq. Finding the total electric field requires integrating the contributions of every single dq element across the entire geometry of the object. Successfully setting up the bounds and coordinate systems for these integrals requires a rigorous mastery of vector mapping. This first principles integration is universally accurate, but it routinely transforms simple physical shapes into daunting mathematical problems. Consider a standard physics benchmark, calculating the electric field at a point near an infinitely long, uniformly charged wire. This diagram establishes the setup. We isolate a tiny charge element, dx, and define the wire's linear charge density as lambda. The field contribution from this slice points diagonally toward our target, meaning the vector must be broken into its horizontal and vertical trigonometric components. Because the wire is infinite, we find a physical shortcut. For every slice on the right, there is an identical, mirrored slice on the left. These mirrored pairs project equal and opposite vertical forces, causing all vertical components to perfectly cancel each other out. We are left integrating only the horizontal cosine components across the entire span of the wire, from 0 to infinity. To actually solve this, the math requires a complex trigonometric substitution, swapping x for y tan theta and recalculating the integral's bounds. After several steps of calculus, we reach the final result. The electric field E equals lambda over 2 pi epsilon naught y. The answer is correct, but the process required pages of tedious trigonometry just to solve for a single straight line. Is there a way to determine the total field without manually summing every individual vector? Instead of summing discrete forces, we can visualize the field as a continuous flow radiating outward in all directions. This shift in perspective leads to the concept of electric flux. We define flux as the number of field lines that pass through a hypothetical surface placed within the field. Mathematically, flux is the product of the electric field and a small element of area, adjusted by the angle between them. By wrapping a three-dimensional closed surface around a charge, effectively enclosing a volume, we can measure the net flow exiting that space. Transitioning from a system of vectors to a system of areas allows us to bypass the complexities of traditional integration. This is Gauss's law. It states that the total net flux through any closed surface is exactly equal to the enclosed charge, divided by the constant epsilon naught. While the law works for any closed boundary, the Gaussian surface, the difficulty of the math depends entirely on the shape we choose. Let's revisit the infinite wire problem, leaving the Coulomb integration approach behind. We construct a Gaussian surface that mimics the symmetry of the wire, a coaxial cylinder of radius r and length h. Notice the result. The field radiates directly outward, piercing only the curved side of the cylinder. The field runs parallel to the end caps, meaning no flux passes through the ends. Since the wire is perfectly centered, the electric field strength is identical at every point on that curved surface. Because the field E is constant, it can be pulled completely out of the integral. The calculus collapses into basic algebra, the field multiplied by the surface area of a cylinder. We equate this simplified surface area to the total enclosed charge and solve for E. We reached the exact same answer as the brute force method, but in 3 lines of algebra rather than 2 pages of calculus. Gauss's law operates by exploiting the geometry inherent in Coulomb's law. This framework can be applied to any standard geometric problem where charge is distributed uniformly. For a spherically symmetrical charge, we choose a spherical Gaussian symphysis, simplifying the integral into the area of a sphere. For an infinite flat plane, we use a cylindrical pillbox where the flux exits only through the end caps. When a physical system exhibits spherical, cylindrical, or planar symmetry, Gauss's law becomes the most efficient analytical tool available. However, Gauss's law is not a universal solution for every calculation. Consider an asymmetrical object, like an irregularly shaped, heavily charged rock. Its electric field lines are completely chaotic and unpredictable. Because the field strength is constantly varying across space, there is no geometric shape you can draw where the field E is constant across the entire surface. Without a constant field value, you cannot pull E out of the integral. The algebraic shortcut disappears, and Gauss's law becomes impossible to solve. Gauss's law rewards those who can identify and utilize symmetry, but when that symmetry is absent, first principles integration remains the only path forward.